observes it, and then acts accordingly. So this is the introduction to it. So basically, as I said, the reinforcement learning agent observes the orbit, all the debris which is coming into its direction. It's looking at all the things and then acting accordingly to make sure that the satellites don't collide. So that's that. Just the mission roadmap for this presentation. Firstly, I'm going to just talk a little bit more about the congestion and communication crisis, then go into the real-world operational constraints. So these are some of the factors that we also decided to think about when we were making our project. The MarsNet solution and the 70% target. So that's our benchmark. Some of the features I included, and of course the live system demonstration and future trajectory and scaling plans. So let's go right in. So yeah, as I said, there's a specific time frame where if satellites are orbiting Mars, in a certain time, we cannot actually access the communications to satellites. And, that brings the risk that if there is, a problem or emergency, you can't actually do anything, and the satellite might potentially collide with something and crash. So that's where, we need to think of adding some kind of, software or something which can actually autonomously maneuver. And I thought that adding, AI models, specifically a reinforcement learning model, would be really, really good. So that's basically the problem and what I'm trying to fix. So that's that. Some of the operational constraints. So these are some of the things that I considered and could be considered in a real world application of this as well. So firstly, I just want to differentiate what the difference is between satellites which are orbiting Earth and what the operational constraints would be if we were to do it in Mars. So in Earth, it's a lot easier for satellites to maneuver because it's very, very close to the command center, and there's appropriate infrastructure for it to move around and have effective communication. Mars is not that case because Mars is way further, and also of course that 4 to 24 minute time frame where we can't access the satellites brings a big operational headache, and that causes potential emergency situations where we can't control it. So that's one thing we have to consider, a difference between satellites which are orbiting Earth and satellites which are orbiting Mars. Another thing is propellant limits. So this is just specifically that we have to consider that fuel in these satellites is a very, very it's a variable which is very limited. So we have to consider that if, let's say, we're maneuvering these satellites, that we don't use too much thrust. If, let's say, we do use a lot of thrust, then there might be a chance that the operation might end early, or the satellite won't even move. So that's the biggest thing. And then another thing is slow stream RL, which is basically saying that since the reinforcement learning model is actually in observing the environment around it, there may be a chance that there may be delays in the information, where the reinforcement learning agent has delays when it's getting the information. So we have to consider that as well in these applications. So these are some real world operational constraints that I considered when we were making this project. So the solution and benchmark target. So firstly, let me just explain the few images I have, and then I'll go into the benchmark target we have. So this is basically the application. As you can see here, this is the live engine that I made. And you can see this is Mars, and these are the moons, and this red stuff is debris, and these are satellites. So here, if you look at the control panel, you can see that there's two versions. There's AI off hits and AI on hits. So AI off hits is when the AI model is actually not being demonstrated. It's not currently being used. And the satellites are just following their default orbits. And as you can see here, the AI off hits got at least 6 hits, and they were averaging around 3 hits a minute. But as soon as we added the AI on hits, we implemented that, we could see that there was no hits in this specific testing cycle, and we had a collision reduction of 100%. So this shows that our AI model is doing really, really good. And that goes back to our collision reduction target, where based on all the testing cycles I've done, I've been averaging around 85 to 100% collision reduction. So the collision reduction target is well ahead. Sorry, the collision reduction is well ahead of our target, which is good to know. Here's our live collision and evasion log. If let's say you want to see where specifically a satellite is getting collided with or getting hit, you can check this out and when it's happening. Another thing is this reward function. I thought to add this because this was a really important thing when I was first making the project. So a little bit context is when I was making these models early on. When I implemented the RL model, what it did is that it developed like this exploit where the satellite started to go out of the orbit in order to avoid the debris. So I had to set up this equation where it said that you had to be on your default orbit. You had to always come back to your default orbit, even though you're thrusting around to avoid debris. So I think this is one of the biggest important features that I had to add in order for my entire application to work as I intended. So I decided to add this as well. A few key. Oh, are you saying something?
No.
Oh, can I continue?
No, please go ahead.
Oh, okay, all right. Yeah. So continuing, we have the key like technical features I added. So firstly, I added a neuro-symbolic shield. So basically, you have like this is kind of like a backup plan you can think. So let's say if the AI model is doing well, but let's say hypothetically that debris gets really close to the satellite. So this shield is basically like its last layer of defense. It completely overrides the AI, and it has a bunch of hard-coded functions which manually make it maneuver out of there entirely, so it does not have the chance of actually colliding. So as you can see, this is a danger distance. So at a certain point, if the debris gets into the satellite's radius at this specific distance, then the satellite will enable this thrust, which is a lot higher than we're going with, and it will basically try to maneuver out of there. Another thing is the per satellite multipliers. You just have to consider that we are using at least 8 satellites, and they're using 3 different orbital planes. So it's really hard to control all of them with one singular AI model. So what I did is I used different AI agents for each satellite, and basically what that does is that these AI agents can now look at their satellite's own environment and act accordingly. And then, of course, the station keeping penalties. This is just like a reward-based system, as I was talking about before, where, if let's say a model starts exploiting or start doing something which is not intended, then we can, of course, add these station keeping penalties, which help to bring back help to teach the AI that this is not what you should be doing. And, that's basically the idea of this. And yeah, we have our live demonstration. Before we go into the live demonstration, do you want me to cover this future trajectory roadmap? Because I think this is my last slide. Yeah. So do you want me to cover this real quick? Yeah. Okay. Sure. So the future trajectory, what I'm aiming for is, I want to add more satellites. Currently, it's very limited to 8 satellites because if I add more satellites, the application starts lagging a lot. And that's not good because if, like, let's say the application crashes, then the entire idea of it just won't work. So currently I've limited to 8 satellites, but hopefully in the future, I want to try to implement at least 50 satellites or a whole system of them. Another thing is, the physics model. Of course, since I made the live engine, it's not going to be as accurate as, a real world application of a Mars orbit. So my hope is that I implement far more features which help to make it as realistic as possible to the actual, physics of the Martian orbit, which we have in real life. And then, of course, PPO SAC upgrade. This is basically just saying that, the Q learning model we use. So that's for the RL agent to basically improve it so that the AI model is completely, completing its task and not having as many problems as the, attempt before. So these are some of the things. And yeah, we can go into the Martian satellite simulation. Okay. Can you see this? All right, perfect. So as you can see, let me just resume the simulation. So as you can see, can you see the satellites are moving around and stuff?
Yeah.
Right. So this is basically the live engine I made. As you can see, this is Mars, and this is the debris and satellites I was talking about. So this is the live engine where the RL agent is actually feeding the information and sending its commands to. So as you can see here, like it's moving around. This is the animation speed. This is basically just saying how fast, like you can control how fast you want to move these satellites. And of course, this is the AI defense off and on toggle. If you want to see how the AI defense is doing compared to what if it was in a default orbit, you can see that. And then yeah, that's it for this specific panel. If you go into collisions, you can see here that it was already running. So this is another test cycle, right? So this is AI off hits, as I explained. This is when the AI is not being implemented, and this is where AI is on. Now, unfortunately, see that this has 2 hits. So this is where we can keep improving, where I want to actually target in my next benchmark to have at least 95%. As you can see here, collision reduction is still great, but you see the AI is still getting hits. So I want to continuously improve that. Live collision and evasion log. Of course, you can see here the things I was talking about, where it's getting hit and what it's getting hit with. So each debris is marked. So this is that. And then the other panel I have is a telemetry panel. This just goes even further if you want to look on what is the problem. Has a bunch of different variables and graphs which you can understand. Altitude trajectory talks about the altitude, where the satellites are, what is the average to that. Threat proximity is just talking about what is the average threat between all these satellites. Avoidance efficiency just compares the AI off and AI on. Shield interventions is just talking about, how many times does that shield, the neuro-symbolic shield feature actually get implemented. So far it's 0, which is good. RL policy exploration, this is basically talking about at what point does the satellite keep exploring and what point does it, keep going in its orbit. And then the cumulative fuel usage just goes back to the idea of how much fuel is being used and how efficiently can we use it. Constellation risk Constellation risk matrix just talks about the current overview of the satellites, which ones are safe, which ones are not. System sync and health. This is talking more about the system in general, how much delay is going on, and how you can just track it based on that. And then if you go further down below, we have a live decision and event logs. This is basically looking at the entire system and just talking about how the system is doing in general and how the satellites are doing in general. So this is the telemetry section. If you would go back, then there's the assistant. So here in the assistant, we have the RL agent queue table. So this is basically explaining how the RL agent works. Each of these code bases is basically each satellite, and it explains the, what specific, action is being done for each satellite. And then if you go further down below, you can see the multipliers of the satellites. Each has a distinct multiplier, and it talks about how farther and closer to the orbit the satellites are moving. And the total steps is how many simulation ticks has the AI been learning through. So that's that. And then last but not least, I have a custom chatbot. So this is basically a chatbot I implemented. If let's say there's a user who's very curious about certain features in the thing, so you can ask, let's say, how does the RL model work in this application, right? So you can ask that, and it will explain to you everything, how it works, where it works, and what you can do to make it better and stuff. Also, customize UI. This is just like a thing I did. You can customize based on whatever you like. So that's that, and that's pretty much all about my application. Yeah.
All right. Really interesting, and you have a lot of in-depth knowledge about this topic. So that's really good. So I have a few questions for you. So my first question is, I saw that there was no intervention to your RL agent, the safety intervention. So have you tested it, or is it not being exercised? Have you thought about it?
Yeah, so of course I tested it. I've had at least like 15 to 20 different test cycles. So in the idea, you're talking about the neuro-symbolic safety
Yeah.
shield, right? Yeah,
Yes.
so it's very 50-50. So sometimes you would see that it's being implemented a lot, and sometimes you would see that it's not being implemented at all, which is in our case. The idea is that it shouldn't be being implemented at a lot, because that tells that the RL agent is actually not doing its job. Because the idea is that that safety shield is basically the last layer of defense. So if you're seeing that happening a lot, that tells you that the RL agent is not doing its job. Now, of course, in my earlier test cycles, when my RL agent wasn't as effective, yeah, I noticed that like it was happening a lot, and it was very concerning. But as the RL agent trains and gets better, it starts to get slower and slower. So yeah, that's that.
Okay, that's a really good answer. All right. So I saw that you wanted to go from 8 satellites to 50 satellites, right? So
Right.
in that case, whenever it happens, what do you think is the first thing that'll break in your program? Like, where's the scalability issue right now?
So currently, the problem is that, let's say if there's 50 satellites being implemented, first of all, we would have to add more agents to that, right? So there would be, instead of simulation, we would have to do simulation and look at the animation, right? So if we add more satellites, the animation starts to break. As you can see, it's very, very slow already, right? So if we add more satellites, the biggest concern I had was that the animations weren't working perfectly, and then they started to lag a lot, and that kind of crashed the entire application on its own. So that's why I decided to limit it on around 8 satellites for now, and see how the system does in general, and then scale from there.
Okay. So and how do you think you'll fix it? Like, how do you think you'll make it scalable? Will you bake the animations or like how?
So what I think personally is that I would need to look at the so there's a specific code file. It's called server.py, which connects everything into this live engine. So the information from this live engine goes to the RL agent. The RL agent's command goes to the live engine. So I think I need to edit that and make sure that like the application can hold 50 satellites, right? Because currently, if you look at 8 satellites, you can see that it's working well. But like, let's say I add 20 satellites, there's a chance that it might completely break because of the lag. Maybe another consideration I could do is switch to a better hosting application, or use a different service which can help to make it more smoother. So that's what I have for now for that.
Understood. Yeah, that'll be a really good approach. Uh, and overall, your project is really good. Like, it's definitely one of the projects that you can take forward and work on it over a long time, and definitely do it, document it, and make it something out of this project. Don't let it just
Right.
die for the program.
Yep.
And yeah, I think that and this is it for the technical part of the interview. There's another
Of course.
panelist in the call right now who will carry on the session,
Sounds
and
good.
that part is more around you and your experience. So, yeah,
Sure.
I'll see you.
Do I have
Great.
to keep sharing my screen?